So when an action potential occurs at a given spot on a neuron, we have opening up of voltage-gated channels at that spot. This is what keeps the action potential moving unidirectionally. So basically, these channels open in waves down the length of the axon. Okay, so it is basically a series of stepwise opening and closing of these channels down the length of the neuron, and this prevents the action potential from moving in the retrograde or reverse direction. Okay, so looking at this illustration here, we can see our neuron. We've got the soma on the left, we've got the length of the axon, we've got the axon terminals. We know that the action potential originates really here at the axon hillock and travels down the length of the axon. And so if we zoom in more closely at what's happening on the down the axon, we can see that there are different sort of segmentations of this neuron. So we open up voltage-gated sodium channels in this blue area of the neuron, whereas the remaining segment is still in the resting state. So we still have a membrane potential of -70 in this yellow area. Then as that action potential travels to the next spot, this previous area, this previous segment is now in its refractory period. And because the previous segment is now in its refractory period, the action potential cannot move to that previous spot. It must continue to move in the anterograde or down the length of the axon, okay? And that's what we can see here in this final part of the image. So panel 3 shows that the previous segment is now back in the resting state. The middle segment is in its refractory period, and the action potential has arrived at that terminal or that distal part of the neuron, okay? So this is what keeps the action potential impulse moving down the neuron and not moving backwards. So the action potential, that should say action, not axon. The action potentials are produced down the entire length of the axon. The conduction rate is typically slow if we have an unmyelinated neuron. So this illustration is showing what's happening in an unmyelinated neuron. The action potential has to go from spot to spot to spot down the entire length of that neuron, okay? Because there are so many action potentials generated, and it must move along from site A to site B to site C, the amplitude of each action potential is the same, but this is going to happen much slower because the action potential has to go from each of those segments to the next, okay? This is in an unmyelinated neuron. So let's just kind of walk through what's happening with this schematic. So we've got the resting neuron, we've got site A activated or having that action potential via the opening of voltage-gated sodium channels. We've got site B still in its rested state. In C, this part of the image here, we can see that the action potential has jumped to spot B or site B, whereas site A is in its refractory period and site C is still at rest. And then in the final panel, we can see that the action potential has gotten to that final site, and site B is in its refractory, site A is at rest, okay? So that's what happens in an unmyelinated neuron. Let's look at what happens in a myelinated neuron. So this is what we just went through. In a myelinated neuron, that myelination helps to provide some insulation, which speeds up the conduction of this neuron. So this is why myelinated neurons are usually thicker. They're usually found peripherally, where the action potential has a long distance to travel. So think about your radial nerve in the upper limbs, your sciatic nerve, that very long, thick nerve in your lower limbs, is typically heavily myelinated to really speed up the propagation of the action potential. And the way that myelin does this is that it insulates the neuron, and there are gaps or openings called nodes of Ranvier. So the nodes of Ranvier allow for sodium and potassium to move across the membrane potential, and they're located about every 1 to 2 millimeters down the length of the axon. So we've got myelin here, And then we've got this spot that's called the node of Ranvier. So this is a spot that has no myelin or myelination. And so the action potential, which was here, doesn't have to go to each of these spots. It's going to jump across this myelin sheath and on to the next node of Ranvier. Okay, so it basically leaps from node to node, and that is how we speed up the conduction via myelination. Right? This is called saltatory conduction. So we've got a heavy concentration of those voltage-gated sodium channels at the area, at that node, at the node of Ranvier, and we have myelin in between each of those nodes, which facilitates the jumping or leaping of the action potential. And we can see that better here, right? So we've got a myelinated neuron. This is a sheath of myelin, right? We've got the nodes in between these openings here, where we have a heavy concentration of those voltage-gated sodium channels. And so the action potential starts here. And just to zoom in and see what that looks like, the action potential starts here, and then it jumps here, right? And then it jumps to the next one. And the spot that was before, so where the action potential was in this image here, is now in its refractory state as that action potential propagates down the axon. Okay. So let's talk about some factors that can speed up the action potential propagation. So one we know is the increased diameter of the neuron. So if we have a thicker neuron, this is going to increase the propagation by decreasing the resistance to the spread of that charge, the spread of that electric signals down the length of the axon. Myelination is another factor that increases this saltatory conduction or this propagation of the action potential. And so if you look at a few examples here in this table to the right, we can see that the general trend is that sensory neurons typically have a smaller axon, a larger axon diameter. Somatic neurons, which are like your muscle neurons, have a larger diameter as well, whereas autonomic neurons to the bottom here, these are going to be involved in smooth muscle innervation, cardiac muscle innervation, glandular innervation. They typically have a smaller axon diameter, and so they're going to conduct much slower than your larger neurons that are involved in moving big muscles, in sensory perception, and so on. All right, and we can go anywhere from a conduction velocity of 1 meter per second, so that action potential can travel 1 meter per second in small neurons like our autonomic neurons, and then it can travel much faster at about 100 meters per second in our bigger neurons, your sciatic nerve, your femoral nerve, and so on.